For our second speaker of the afternoon, we have Hana Dal Poz Kourimska, and I apologize if I'm mispronouncing. She's going to talk about type bounds for learning homotopies. So please.
Thank you. So let me start by thanking the organizers for letting me present here remotely. And I apologize if there are any background noises. My baby is just about to go to sleep, so it might get a little loud. Okay, so I'm very happy we had this short discussion just a moment ago with Sarah about radii, because my talk is all about the radii, actually. What is the task that we are tackling? We start with a set, which we'll call S, and it's a subset of the Euclidean space, and a point cloud or a point sample, which we will call P. And straightforward task is to recover the homotopy type of the set S from the point cloud P. Just as a note, we will have this example recurring in the whole presentation, and this set has a homotopy type of a circle. So the question is, can we recover this circle from the point cloud P? There is a method to recover some topological information from point cloud P, and this audience knows it probably better than I do. Essentially, you want to pick a radius R, then you look at the R offset of the points P, and then you can use some computational machinery to calculate the homotopy type of this offset. So that is easy, but of course the question is how to choose this radius R. And here I chose various radii, and you can see that if the radius is too small, you only pick up the points. So potentially you would have too many connected components, let's say. And then in my example, actually there is a radius here in the third picture where you recover the correct homotopy. And then once the radius gets too big, everything is contractible, and you essentially gain no information about the underlying homotopy again. So the task of today is, well, if you have these two sets, the set S and the point cloud P, find a radius R such that the R offset of P recovers the homotopy of S, and more concretely, does such radius R always exist? Well, the answer is, short answer is it depends, and it actually depends on two sets of parameters, let's say. It depends on the set S itself, and then it depends on how good is your sample. So in my talk, I will first talk about the state of the art. And then I will talk about essentially how we improve on it. I will first discuss the conditions that we set on the sample P, and then the conditions that we set on the sample, on the underlying set S. And I will spend a little bit more time talking about what is the reach of the set, although probably many of you know the notion, but that's actually the biggest improvement, or in my eyes, the biggest improvement on the state of the art is that we only consider sets of positive reach. Okay. Then that will be already towards the end of the talk. I will state the main theorem of the paper I'm talking about and contrast it with the state of the art. And if time allows, I will tell you a little bit about methods that we used to tackle the same question in the Riemannian setting. So essentially throughout the whole talk, I will be talking about subsets of the of the Euclidean space, but we also have the same theory for subsets of Riemannian manifolds, but I think it would be too much for the talk. So if I have a bit of time, I'll touch upon it, and if not, too bad, you'll have to read the paper. Okay, so the state of the art. I mentioned very, very few papers. There are many more out there, but for the sake of time, our paper, as it's apparent from the title of the talk, bases heavily on this work of Niyogi, Smale, and Weinberger, which is called where they search for the homotopy of submanifolds from some random samples. And the conditions that these authors have on the set S is that it is a C2 submanifold with positive reach. The next paper I want to mention is this one by Wong, topological inference of manifolds with boundary. And there, as the title says, they generalize the notion, considering not only C2 submanifolds, but also C2 submanifolds with boundary. And in fact, in this paper, they use the result of Niyogi, Smale, and Weinberger to tune the conditions on the boundaries. Then I wanted to mention these two papers, which are like in a little bit of a different flavor. These two papers consider much more general sets, namely compact subsets of the Euclidean space, but they do not. They consider so-called positive mu reach, which is yet more general than the reach, but they do not obtain any time bounds on the sampling parameters, so on the parameters on the sample P. So our work is somewhere in the middle between the first two and the second two papers. Okay, the conditions. Maybe let me get the time since I can see. So the conditions on the set S will be that it's a closed set and it has a positive reach. And the sample P will have to be close enough and dense enough. I'll start by explaining what close enough and dense enough is, which is, I think, simpler. And then I will talk about the reach. So close enough means that if I start with my set S, then I take a parameter delta, and I consider the delta offset of this set S. And then my sample P is delta close to the set S if it's within this offset. Dense enough is vice versa. You start with the point sample, and you choose some parameter epsilon and consider the epsilon offset of the set P. And then the point cloud is dense enough if the set S lies within the epsilon offset of the point cloud. Okay, so that's pretty straightforward. This is also called the one-sided Hausdorff distance from one set to the other. I have to say I never remember which one do you start with and which one do you end up with, but it's important to remember that we operate in our setting with two parameters. One is delta and one is epsilon, and they mirror somewhat the closeness of the point cloud and the density of the point cloud. Okay, now let's talk about the reach. So the essential ingredient of our proof, actually, of our main theorem is the map, or let's say map, that's called the closest point projection. And what this map does is that if you take a point in the ambient space, it searches for the closest point on the set to this point. If your point lies on the set, then of course the image of the map is the set, is the point itself. But then there is a special set of points in our ambient space where there is no unique point that is closest to this point. And this set is somewhat of a troublemaker set. It's called the medial axis. And then the reach is defined as the minimum distance from the medial axis to the set itself. All right. Let's quickly go through a couple of examples of sets and their reach. I like to think about the reach as something that measures how bad the cavities are or how narrow the cavities are. because the narrower the cavities, the more problematic it is to pick them up using computational methods, or assuming that you have some noise, then suddenly you can run into trouble. So our first example is any convex set. Those are the nicest sets. So somehow the bigger the reach, the nicer the set. So convex sets have no medial axis, and thus the reach is infinity. The second example is a sphere, or a circle in my case. That's second best, I would say. The medial axis of the sphere is the center of the sphere, and thus the reach is equals the radius of the sphere. Then we have the square. So somehow from a circle to a square, one would say, well, how much worse can it get? Actually, a square is one of the worst sets to consider in these terms, because the medial axis consists of the diagonals, and thus the reach is 0, because at the end of the diagonals, the medial axis actually touches the set itself. And then if we have some, let's say, arbitrary set with a bit of a dent, then the medial axis is, as you see on the picture, I didn't dare to name it, but the reach is then sort of the bottleneck of the dent. So the part where the set gets globally very close to each other. Okay. So I hope this gives you some intuition about the reach. So reach is defined for closed sets, which is great because this is a very general condition. And why do we need the reach in our example or in our theory is because if we avoid the reach, then we can use this this closest point projection and retract the offset, this blue offset of the set to the set itself. And that is the main ingredient of our theorem. Okay. So let's recap a little bit. What do we have? So we are given a set S and a sample. And the question is, for what radius does the R offset of the sample recover the homotopy type of the set S? And the conditions in our paper are on the set S that it's closed and it has positive reach. And on the sample P is delta close, so close enough, and epsilon dense, so somewhat dense enough. And because we want to use the closest point projection, we assume that the parameters delta and epsilon are smaller than the reach. Okay, so these are our conditions. And with these conditions, let's have a look at what the theorem says. So the theorem says that if epsilon and delta satisfy a certain condition, then there exists a radius R such that the R offset of P deformation retracts onto the set S along the closest point projection. And the great thing is that this gray box is actually just a linear condition on epsilon and delta. Furthermore, we can give you, not only can we guarantee that this radius exists, but we can also give you a concrete radius which hits the right homotopy type. Even better, I'm selling our results. This bound is tight. I will actually show you an example or counter example as you wish, which demonstrates the tightness of this bound. We furthermore proved that if we add an extra condition on S, namely if S is a manifold, and a condition on epsilon and delta, then the same holds for a better bound. And this bound is also tight. We also have a counterexample or example that demonstrates this tightness, but I will not demonstrate it to you today. But we have an excellent video that demonstrates this example and also demonstrates why this example shows the tightness by one of the co-authors of the paper, which we'll hopefully be submitting to the sausage media. So stay tuned for that. It's really, I didn't do it, so I can say that it's absolutely amazing what my colleague did with Blender. Okay, let's have a look at the tightness of the bounds. So this is just a little example. So what do we have? So we say that if epsilon and delta are less than r, where r will be the reach of the set, and they break the condition that I had before, so I just twisted the sign, then we can find an S whose reach is exactly this r, and the sample P who is epsilon delta closed and epsilon dense, such that we can never find a radius r where the offset would have the same homotopy. So we have no chance of recovering this homotopy. Okay. So this is the set S. The set S will consist of sort of finite union of annuli. The number of annuli depends on the epsilon and delta, but it will always be finite, as we show. It's a technicality to show that this exists. It is not connected, but one could sort of squeeze in little tunnels between the annuli to make it connected without breaking any other of the conditions. And then the set P looks like this. So for each annulus, there will be a circle in the center, let's say, of the annulus. And then in the center of each annulus, there will be like 2 points chosen in a very particular manner. And these 2 points will be like further and further away from each other. And this is important for the counterexample to work. Okay. So let's see. So here you see 3 of the annuli, and we started already growing the offset R. So actually the pink set is already the offset, and the annulus is already hidden behind or below it. So maybe actually let's go back. You see that the homotopy type of the set S is just sort of the number of the annuli, like the first homotopy. The zero homotopy as well. So in this example, you can see that in the first annulus, the balls around the 2 points have already touched the offset of the annulus, and the hole that one would almost expect is already closed. So in the first annulus, we only have 1 loop, which would correspond to the homotopy type of the annulus of the set. But at that exact point where this hole closes, in the second annulus, which is now kind of the important one, we have 2 loops, because the 2 balls around the points closed, they touched, but they didn't yet sort of expand to the right to close the little hole that is in between the 2 balls and the annulus. And at the same time, in the further sort of right annuli, the balls around the 2 points didn't touch yet. So there in the other annuli, we still have a homotopy type of 1 loop. And this goes on basically. Then when we grow the radius R even further, so that the hole in the middle, in the center annulus closes, that's exactly the point where the balls on the next annulus start touching and create an extra loop. So at any point, the number of loops of the offset will be 1 higher than the number of loops of the original set. And thus we have different homology, and thus we cannot have the same homotopy type. What I'm sweeping under the rug a little bit here, well, very much here, is what happens when the radius is very small and when the radius is very, very large. For that, I would invite you to have a look into the paper, but it's all set in such a way that even there you cannot recover the homotopy type. Okay, in the last couple of minutes, let's talk about the state of the art. So for that sake, we assume that the reach of the set is 1. And we plot our inequalities for values of delta and epsilon. So you can see that we get 2 regions. The blue region corresponds to the assumption, the general assumption on the set S, and the yellow region corresponds to an additional assumption that the set S is also a manifold. And the striking thing is, the striking thing is actually that the bounds are tight. So really, these are all the values of delta and epsilon that you can expect to have, with which you can recover the homotopy type of the set S. And to contrast it with the state of the art, these are the 2 values that Niyogi, Smale, and Weinberger considered in their paper. So essentially, the upper dot is when epsilon equals delta. There they actually reach the maximum possible value in that direction, in the diagonal direction. And then they considered another part where delta is 0, meaning that the sample is sitting actually on the set S. And you can see that in that case, you can actually do slightly better if the set is, well, general set, and a lot better if the set is a manifold. Okay. Very briefly about Riemannian manifolds. So the challenge when you sort of move from subsets of Euclidean spaces to subsets of Riemannian manifolds is that all of a sudden you don't have a unique path connecting 2 points. And this means that essentially you need a new definition of medial axis. There are definitions of medial axis out there for Riemannian manifolds, but for our purposes, we needed to create yet another one. So yeah, we did that. It's one of the features of the paper is that, well, there is yet another definition of medial axis. The second thing that we are using in our paper is comparison theory. This basically says that in order to get some reasonable information about the manifold, which is called M, is you start with the manifold and then you look at the sectional curvatures of the manifold. You have a look at the lower bound of them, and then you can use this to project whatever information you have on the manifold into the space of constant curvature with that sectional curvature. I have a little triangle here with 2 edges, B and C, and an angle between them. And then there is the comparison theory, which tells you, well, I cannot tell you exactly how long A prime is, so the 3rd edge between vertices 2 and 3, but I can lower bound it by sending the information, upper bound it by sending the information over to the space of constant curvature. And we use this trick a lot. In the space of constant curvature, the situation is very much like the situation in the Euclidean space. And yeah, with these lower bounds, you can actually translate the results back, and we get the same results. So we have subsets of Riemannian manifolds. We also have submanifolds of Riemannian manifolds, and for both of these cases, we have tight bounds, assuming that the tightness on the bounds of the sectional curvature, that the bounds on the sectional curvature are also tight. So somewhat one would say we have tight bounds in the spaces of constant curvature, and then you can use the comparison theory to get the rest. Okay. Great. To summarize, we can recover the homotopy type of a set S from a sample point if S is closed, it has positive reach. the sample, the point cloud P is delta closed and epsilon dense in S, and then we have conditions on this, that what this delta and epsilon should be. Our bounds are tight. We get even better bounds if we know in advance that S is a manifold, and we get similar results for subsets of Riemannian manifolds. I have to say that the bounds look a little uglier in that case, but we have concrete bounds. All right, and that's it. Thank you very much for your attention.
Were there questions?
Here, I'll ask one. So you said for the Riemannian setting, when you generalize it, that you had to sort of decide which version of medial axis to use. So the magic of Euclidean space is that there's 4 different formulations and they're all the same. What did you define the medial axis as in the Riemannian? Did you use or did you do something local with geodesics or what?
We use the cut locus.
Okay.
Yeah. And then essentially, yeah, we use the cut locus, and then we define, so cut locus would be like generalization of local feature size, and then we just took the minimum of that.
Thanks. This was really good stuff. This paper by this NSW paper, did they work in the same setting, like using the reach and so on, or I'm trying to remember what the setting was there. Was it curvature or?
Well, they do use reach because as in they do use reach. The reach is in the conditions of the theorem. So they I mean the sets that they consider are C2 manifolds with positive reach. But I think they essentially work with the like differentiability. So that, I mean, there is a reason why they take C2. Yeah, I'm not sure exactly if they deduce the conditions from the curvature, but yeah, I think so.
Was it slightly different type of conditions from what you had?
Yes, yeah.
If I remember correctly, they use reach, but they had a relation between curvature and the reach for the smooth manifold case.
Okay.
So they derived.
I felt like there was something about the.
Yeah, I think the main contrast is that we have this like delta and epsilon sort of to classify the, or to classify the goodness of the point cloud, and they don't have that. Like they really only consider like as like Hausdorff distance, so where epsilon equals delta, and then when delta equals 0, so like sort of very special situations, let's say, in comparison to our results. But they also work with like there is like random samples, or there is some kind of like the approach is really slightly different than ours.
Thanks.
So often in this type of work, people ask, at least I will be asking, to use it, I have to compute the reach. Otherwise, you don't get the bound of epsilon delta. So I know it's very difficult to compute reach, but do you have any suggestions?
No. I don't know. So the way the way I like to think of it in applications is that say like I know the set and I also know what the reach of the set is, and then I just have to send you the point cloud and the information, the number, which is the reach, and then you will know from that what epsilon delta you can, well, you already have. Okay, maybe I didn't think that through exactly, but somehow I like to think of it that like one part knows all the information, and then you sort of want to move this information over somewhere else. And for that you only need like finite amount of information. But yeah, back to your questions. No, I don't know. I don't know how to compute the reach.
Well, in that case, let's thank our speaker again. Thank you.
Thank you very much.